Hello everyone, welcome back to Mechanics and Materials. So in the previous two classes, we have talked about how to use two big tables and the superposition method to solve the deformation of simple or combined beams subjected to combined loadings. The deformations can be deflections or slope at a random point. The slope is a local tilting angle. Then today we will talk about indeterminate problem, indeterminate beams. I know many of you hate this word, indeterminate, because in our previous chapters, the indeterminate problems were always the most difficult part of the chapters. And in our chapter 3, axially loaded elements, and chapter 4, torsional elements, we had both indeterminate problems. So today you need to recall your memory so you can understand the indeterminate beams better. So that's why I featured this music, Memories from Maroon 5. Okay, you need to really recall your memories regarding the principles of solving indeterminate axially loaded elements and indeterminate torsional elements. So that is our objective today, to solve the reaction forces in indeterminate beams. So first of all, let's review the basic principles of indeterminate problems. What is indeterminate? So now I need you guys to recall your memory. What is indeterminate? So in a system, if we can solve the problem, solve the internal forces and reaction forces, just using free body equation, a free body diagram, and equilibrium equation, then that is determinate. So if we have more unknowns, more reaction forces or internal forces than the number of equilibrium equations we can write, so that is indeterminate problem, meaning that you cannot solve the internal or reaction forces simply based on equilibrium equations. Okay, so how to solve indeterminate problems? Since we need at least the same number of equations as the number of unknowns to solve them simultaneously, or if you want to solve them, so you have to find out additional equations. And our solution was to write additional equation based on compatibility conditions or geometry, right? So here I give two examples. The left one is a indeterminate axially loaded system. So in this example, actually you can see that you have two bars connected to each other while they are fixed at two ends. If you remove any one of them, this is a determinate problem, right? If you remove the left restraint, you will see they can simply solve it. There's no internal force in bar 1, and in bar 2, the magnitude of internal force equals P. Right? So it's simple to calculate, to solve. And now you have the two ends of this system fixed. So this is an indeterminate problem. As we talked about a lot of times before, to solve it, to solve the internal forces, then you can just cut it from here to write a F1. This is the internal force in bar 1. Cut it from here, you get a F2. This is the internal force in bar 2. So you can write a equilibrium equation that is negative F1 plus P plus F2 equals 0. So here you have only one equilibrium equation, but you have two unknowns those are F1, F2. Right? So you have no way to solve this equation. To build the additional equation, we need to go to the compatibility conditions. So what are compatibility equations in this case? Since two ends of this system have been fixed, so there is no overall deformation or elongation allowed. Right? So here, if we say the potential deformation of bar 1, this is delta 1 due to F1, and then Now here we have a delta 2, that is the potential deformation of bar 2 subjected to F2. Right, this 2, delta 1 and delta 2, they should meet a compatibility equation. That is delta 1 equals delta 2, right? No, of course not. Right, we have two types of more than two types of compatibility conditions, but in this case, it should be delta 1 plus delta 2 equals 0. Since two ends are fixed, there should be no overall deformation. Right, so you can extend this equation, then you get F1 L1 over E1 A1 plus F2 L2 over E2 A2 equals 0. So this is our equation 1, and here is your equation 2. So two equations, two unknowns, so you can solve this problem, solve the F1, F2 at the same time. Similarly, in the second example, you have an indeterminate torsional system. And here, again, if you want to solve the T1 and the T2, the two internal forces in the system, again, you cut it from here, then based on the right-hand rule, so you have T1, and here you have T2, and in the middle at point B, you have a TB. So what is the direction of TB using your right-hand rule? So here you have TB, right? So the equilibrium equation can be T1 minus T1 plus TB plus T2 equals 0. So similar to this situation, right, you have one equilibrium equation, but two unknowns. You can't solve it. Then we need to turn to the compatibility conditions. Again, here, since two ends are fixed, the overall angle of twist will be 0, right? Meaning that phi 1 plus phi 2 equals 0. Okay, the phi equals what? TL over GJ, right? So based on this, you have another equations. You can build another equation. Okay, in this slide, I give more examples. Right, you can see 4 indeterminate axially loaded systems and 4 indeterminate torsional systems. Okay, let's analyze them one by one. To try to write the compatibility conditions together. Okay, in the first case here, we have analyzed it. So the compatibility condition could be delta 1 plus delta 2 equals 0. Right. So how about the second case here? You have two bars. Right, there's a bar 1 and a bar 2, but there is a gap between them. So when you add the load, you see here the P1 or P2. Okay, you can add any one of them. Then this load has to close this gap first before touching the second, the other bar. Right, so there is a gap between them. The forces can have to be big enough to close the gap so that this problem is meaningful, right? So in that case, the compatibility condition can be written as delta 1 plus delta 2. So what is the overall deformation in this case? It's not 0, right? Not 0. The overall value should be the gap. Then how about the third case? The third case is a steel reinforced concrete column, like we talked about this in our earlier lectures. Right, this reinforced concrete, meaning that these two phases, steel and concrete, are perfectly bonded to each other. This also works in other laminate composites. Right, these two phases are perfectly bonded to each other, meaning that no interfacial frictions or interfacial sliding is allowed in our assumption, right? So if we have the deformation of steel and the deformation of concrete, well, these two things, they always equal to each other. They are always equal to each other, right? Since no interfacial sliding is allowed, so they will always have the same deformation. So this is the compatibility condition in this case. How about the fourth case here? Okay, we have the bar 1 here and bar 2 here, and they will have a delta 1 and delta 2. So if we assume that the bar ABCD is rigid, so when the load P is added here, this rigid bar will be turned downward about A, will turn in this way, right? So it will have a overall deformation like this. Then here will be your delta 1, and here will be your delta 2, right? So what kind of compatibility equations you can solve here? You can write here. This based on the similar triangles, right? We have similar triangles here. The smaller one and the bigger one. You can see that these two delta, the two deformation values belong to this smaller triangle and the larger triangle, respectively. So based on this, we can write a compatibility equation that is delta 1 over A equals delta 2 over what? We need a length here. So in this case, since delta 2 belongs to the biggest triangle, right? This you need to write here A plus B plus C, right? So here this A is actually AB, and here the A plus B plus C is actually AD, right? So those are these possibilities of compatibility equations that we can write in indeterminate actually loaded elements. On the right hand side, we have 4 cases of indeterminate torsional elements, torsional systems. Okay, the first case we already analyzed, so you can write the phi 1 plus phi 2 equals 0. And all of these 3 cases as shown here, they are actually very similar. And the first case and the second case, you have a core. Well, let's just see, the core is 1 and the skin is 2. Here also the core here is 1 and the skin here is 2. Right, the core and the skin are perfectly bonded to each other, so no interfacial sliding, interfacial relative rotation is allowed. So that is to say, the equation can be written as, in both of these 2 cases, your phi 1 and phi 2 actually equal to each other. Okay. This case has been tested, and the third case has also been tested in our exam number 2, right? So the last case, if you look at this part, cut this part off, it's actually the same as the above case, right? The only difference is that you have the element 2 and element 4, the skin. Right here, the compatibility equation can be written as phi 2 equals phi 4. Okay, those are the possibilities. And so today it's our section 6.4. We will talk about the indeterminate beams. Okay, if you understand all of these cases, it will be simpler to understand the indeterminate beams, since the basic algorithms to solve indeterminate beams will be very similar. Okay, here in this slide, first of all, let's look at this simple indeterminate beam system. The example is here. You can see here in this example, you have a cantilever. If you do not have this roller B, if we remove this roller B, it will be a determinate system, right? It's a one cantilever beam with a concentrated load. So you can simply determine the deflection at any point on this cantilever based on our tables. Right? So you can split it from here, and you can solve the deflection at any point. Then this second part will be keeping straight. So you will get an angle. So you just calculate the slope at this point. So you can calculate even the deflection at the free end. Right? This is based on our previous 2 lectures. So you can solve any problem in this system. But unfortunately, here we have a roller B. Right? We have a roller B, so making it an indeterminate problem. So you cannot solve everything just based on these 2 tables. You have to do more work. So to solve it, we need to follow these several steps. So in step 1, you release the redundant restraint. In this case, obviously, the roller B is the redundant restraint. So you remove it and replace it with an unknown force, that is By. Since it's a roller, you have only one vertical reaction force, right? That is the By. Replace the roller B with the By, as shown here. Then you split the structure into simpler parts. Right? Those will be what we did in the previous 2 lectures. Right? Just split it. In this case, you have 2 loads, 2 concentrated loads. One is the P in the middle, and the other is the By at the free end. So simply, you can split it into 2 cantilevers. One is subjected to concentrated P in the middle, and the other one is the concentrated load By to the free end. So based on these 2 simple cases, so you can solve delta B1 and delta B2. Then the compatibility equation would be what? The calculation of these 2 deflections is step 3. Right, then in the last step, you will apply compatibility equations, compatibility conditions. Then you can determine the unknown force. So what is the compatibility equation in this case? Well, this is our boundary condition, roller support, meaning that at this point, the overall deflection will always be 0, right? Delta equals 0. So that is to say, in this case, you will have delta B1 plus delta B2 equals 0. So this is the compatibility equation. So based on this, we can solve the reaction forces. And here you have a table. The table summarizes the original restraint, like the fixed end, the roller support, and pin support. And then you have the released restraints. In these 2 cases, you have 1 reaction forces, that is the Ry, only in y direction. And in this case, you will have a bending moment M plus a pin support. Right? So the deformation that can be considered for compatibility include 2 possibilities. Right? This the one is delta, as we just analyzed here. You have delta B1, delta B2. Right? The other possibility is theta, right? The slope, as written here. So in the step 3, when you determine the deformation at released restraint, you can determine the displacement for released pin or roller support. That is, in this case, the one example is here, right? It's at the roller support or pin support, you can determine the displacement and perhaps summarize all of them together. You get a 0. Right? This is a compatibility condition or boundary condition. And you can also determine the slope for released fixed support. That is to say, if you want to solve the problem from this end, from the fixed end A, the additional equation that you can write can be the slope. You can focus on slope, since at the fixed end, no matter how this cantilever will be bended, the slope at this point will always be 0. Right? Theta equals 0. But those are the normal boundary conditions that you can use. You can leverage to write the equation, which help you solve the reaction forces. Well, later we will have several examples that will help you understand how to solve the reaction forces in indeterminate beam systems.